9.10 Lesson 3 Taylor and Maclaurin series. Our objective for today is you'll be able to find a Taylor series for a given function by using the basic list of power series for elementary functions on page 682 of our textbook. So these power series are listed on page 682 of our textbook, and we would like to use this opportunity to review what we've learned since section 9.9. So the power series that you see, the ones that I'm marking right now, we actually came up with these in section 9.9. So we're going to have section 9.9 in red. And the power series that I'm going to mark in green are the ones that we've already seen from our homework last night and our lesson yesterday. And they're from section 9.10. And you'll see the power series for e to the x tonight. It's also from section 9.10. And this is called the binomial series. That is also from section 9.10. And after you do the binomial series, you can do some integration to find the power series for the arcsine function. So let's briefly review what we did in 9.9 to come up with the power series for the functions 1 over x, 1 over 1 plus x. For those two, what we did was we used the convergence of a geometric series theorem. If you have a geometric series, we know it will converge to the sum a over 1 minus r when the absolute value of the common ratio is less than 1. And with these two functions, we were able to write them in this form for a particular center. For this function, we use the center c is equal to 1. For this function, we use the center c is equal to 0. And once we were able to algebraically manipulate those functions to fit this form, we were able to represent them with a geometric power series. And then we came up with our power series for the natural log function by recognizing that the natural log function is the indefinite integral of 1 over x dx. And that would give us the natural log of the absolute value of x plus a constant of integration. And in section 9.9, we took our power series for 1 over x centered at 1, and we integrated that to come up with our power series for the function natural log of x centered at 1. And if you look at the intervals of convergence, you can see that they have the same radius. However, the power series for natural log of x also converges at x is equal to 2. And we also found the power series for arctangent of x by integrating a power series for the derivative of arctangent of x, which can be manipulated algebraically to fit the form a over 1 minus r. So that's what we did in section 9.9. Yesterday, we looked at how to come up with a Taylor series that represents the function sine of x, and we began as follows. We began by using this definition of Taylor series to come up with a Taylor series centered at 0 from the function sine x. So we derived, using this definition, we derived a Taylor series centered at 0 from the function sine x. We then determined its interval of convergence by using the ratio test. And then we used theorem 9.23 to show that the power series derived from sine x will in fact converge to sine x on its interval of convergence. And yesterday we discussed why that was necessary for us to do this particular step using theorem 9.23. Having done that, we came up with this power series representation for the sine function on this interval of convergence, all real numbers. And a similar procedure is employed to come up with this power series representation for the cosine function, also for all real numbers. And you do the same procedure to come up with a power series representation for the function e to the x on this interval of convergence. So we're coming up with these power series for these functions by using what we learned yesterday. So so we came up with that in section 9.10. And as I said, we will look at the binomial series, which we will also do using the methods that we're learning in section 9.10. And then there's also the arcsine function and its power series, but you need to come up with this first. So what we'd like to do for today's lesson is use the power series for elementary functions that we just looked at, and you'll be able to find Taylor series for a given function by using the basic list of power series for elementary functions that we just looked at from page 682. And the way we'll do that is as follows. These are the two examples that we'll look at today. The function that we have here is sine of x squared, and the second function we have is the cosine of the square root of x. Of course, from our basic list, we have power series that represent sine x and cosine x. So how can we get power series that represent sine of x squared and cosine of square root of x? This is a composition of two functions where the inside function is x squared and the outside function is sine x. And what we have here is also a composition of two functions where the inside function is square root of x and the outside function is cosine x. So it turns out that we can just use the power series for sine x and cosine x and simply substitute x squared in place of x in the first example and square root of x in place of x in the second example. You may recall these operations from section 9.9, operations with power series. So if you have a power series for a function f, you can evaluate that power series, for example, at x to the n power. And if you have sine of x squared, then you have sine of x to the second power. And if you have cosine of square root of x, then you have cosine of x to the 1/2 power. So we've actually seen this in section 9.9. Also, there are other operations you can do with two power series, such as adding or subtracting them, or multiplying by a constant, multiplying the argument of the power series by a constant k. In addition to that, you could also do multiplication or division of two known power series, or even differentiation or integration. So today we'll be looking at composition with known power series. That's what we'll be looking at today, composition with known power series, but you could also do addition or subtraction of two known power series, multiplication or division, which we will look at separately in a different lesson, and differentiation or integration. So here is our first example, and you may remember this from your most recent open resource self-assessment. It was one of the problems, and you wanted to find just the first two non-zero terms of the Taylor series for this function centered at 0. And it was a lot of work when we were trying to find the first two non-zero terms of the Taylor series centered at 0 for the function cosine of x squared using the definition of Taylor series, because you would have to find derivatives of the function, and as you may remember, it became quite cumbersome to find derivatives after a while because you have a composition of two functions, so just finding the first derivative is not too bad. The derivative of cosine is negative sine, so you have negative sine of x squared, and then you find the derivative of the inside function, which is 2x. But now if you want to find the second derivative, you have to use the product rule, because you have a product of two functions, and not only that, but your second function is a composition of two functions, so you have to use the chain rule for that. And then it becomes even more complicated and cumbersome as you try to find the third derivative and the fourth derivative. So today we're learning that you can bypass that because you already have the power series for cosine of x, and you can just take the power series for cosine of x and replace the x in there with x squared. So here we have the power series for cosine x. The interval of convergence is all real numbers. And we're going to go ahead and write that down here for our reference. So we have cosine of x is equal to 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial minus x to the sixth over 6 factorial plus x to the eighth over 8 factorial, and so on. And the description of the nth term would be negative 1 to the n, x to the 2n over 2n factorial. And of course it keeps going after that because this is an infinite series. So that's what we have for cosine. So all we have to do now to find the Maclaurin series, which is a Taylor series centered at 0, for our function is replace the x in cosine of x with x squared. So what that means is you'll be replacing every single x in the power series for cosine of x with x squared. And you will also do the same in the description of the nth term of the power series for cosine x. You will replace that x also with x squared. So when we do that, we have the following. We will have cosine of x squared is equal to 1 minus, we will have x squared squared, which will be x to the fourth over 2 factorial, and compare these two terms to the first two non-zero terms of the Taylor series centered at 0 for cosine of x squared from your most recent ORSA, and you'll see that they should be the same. And then we have plus x squared to the fourth, that would be x to the eighth over 4 factorial minus x squared to the sixth, that would be x to the 12th over 6 factorial plus x squared to the eighth, that would be x to the 16th over 8 factorial, and so on. And for the nth term, you're going to have x squared to the 2n. You have the power of a power, x squared is raised to the 2n power, so you can multiply the exponents. 2 times 2n is 4n over 2n factorial, and of course it keeps going, and I need to write the plus sign there, and it keeps going. So if I wanted to represent my power series using sigma notation, I would simply write from n is equal to 0 to infinity, and the nth term would be negative 1 to the n times x to the 4n over 2n factorial. If you wanted to, you could show that the interval of convergence for the power series that we just found for the function cosine of x squared is all real numbers by using the ratio test as you see here on this screen. So I said we were going to look at sine of x squared, but we actually looked at cosine of x squared, but they're done the same way. So we'll consider this done because we did a similar problem. And now we'll take a look at sine of the square root of x. We'll switch the functions cosine and sine. So here we looked at, instead of sine of x squared, we looked at cosine of x squared, and now we will look at sine of the square root of x. We want to find the power series for the function sine of square root of x. So we begin with the Taylor series centered at 0 for the function sine of x, and the interval of convergence is from negative infinity to positive infinity. So let's go ahead and write that. So we have sine of x is equal to x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial plus and so on until you get to the nth term, negative 1 to the n times x to the 2n plus 1 over 2n plus 1 factorial, and you keep going after that. The interval of convergence is all real numbers. So to find the power series for f of x is equal to sine of the square root of x, all we have to do is look at the power series for sine of x and replace x with square root of x. Wherever we see x in every single term, and also the description of the nth term, we will replace with square root of x. But of course, you can write square root of x as x to the 1/2 power. So when we do that, we will have the following. So we will have x to the 1/2 here minus x to the 3/2 over 3 factorial plus x to the 5/2 over 5 factorial minus x to the 7/2 over 7 factorial. And then for the nth term, you'll have negative 1 to the n times x to the 1/2 to the 2n plus 1 power over 2n plus 1 factorial, and it keeps going after that. Again, what you have here is the power of a power. So if you choose to, you could go ahead and multiply the exponents, or you could also represent this power series in an alternative format. If you, for example, did not want to write the square root of x as x to the 1/2, you could have just left it as a radical expression, and if you'd done that, then you would have the square root of x minus the square root of x to the 3rd power over 3 factorial plus the square root of x to the 5th power over 5 factorial minus the square root of x to the 7th power over 7 factorial, and so on. And in that case, the description of the nth term would be the square root of x to the 2n plus 1 power over 2n plus 1 factorial, and it would continue. And if you choose to do it that way, then you would simply write the nth term as follows. You would start at n is equal to 0 and go to infinity, and the nth term will be negative 1 to the n times the square root of x to the 2n plus 1 over 2n plus 1 factorial. When you consider the interval of convergence, you have to be mindful of the fact that our function f of x, the domain is not all real numbers because the inside function is square root, and you can only take the square root of non-negative numbers. For that reason, the interval of convergence, it is all x in the domain of the function, which is restricted to non-negative numbers. So today we looked at being able to find a Taylor series for a given function by using the basic list of power series for elementary functions on page 682 of our textbook.